Welcome to module number 5 in this RISE 101 module series. My name is Griffiths Atungulu, Director of the Axial Rice Processing Program. I'm an Associate Professor and Agricultural Engineer. My area of expertise is in grain processing and post-harvest systems engineering. I'm housed here in the Department of Food Science with the University of Arkansas System Division of Agriculture. In this module number 5, we are going to discuss the concept of rice drying fund selection. We are going to talk about the type of funds that are available out there, and then we'll go through the selection procedure whereby we look at a few calculations to help us understand more about how to go about the selection process. So let's start by describing what funds are. Funds are devices that are used to push air through the grain mass. And drying funds are rated to move a certain volume of air at various static pressures, and the lower the static pressure, the larger the volume of air that fund can move. Grain funds are classified as axial flow funds or centrifugal flow funds, and these are based on the mode of inlet and exit of air from the impeller. The first diagram here illustrates what the axial flow funds look like. Now, this fund utilizes a propeller wheel that's mounted directly to the motor shaft, and thus they develop very high speed and are often very, very noisy. Most often, they are used when we need to have high airflow rates, but to overcome low static pressures. Sometimes they are incorporated with straightening vanes that are used to increase the efficiency and also increasing the kind of static pressures that we can achieve. This type of funds can give us up to about 5 inches of water in form of static pressure. Now, there are two types. There's the vane axial and there's the tube axial, as this diagram illustrates. Those differences just emanate from the position at which the motor is located relative to the shaft that is driving the impellers. The centrifugal funds provide relatively constant air volume over a wide range of pressure with a practical limit of up to about 9 to 10 inches of water. With this kind of funds, it's possible to have special designs that can help us overcome some higher static pressures. And they are highly recommended for drying rice when the static pressures are higher and in excess of those that can be achieved by axial flow funds. There are various types. We have the low speed type that can go at about 1,750 RPM. They come in two types. There's the single and double outlet type. And then we have the others which are rather high speed inlet. And these ones can give us an RPM of up to about 3,500. Now, often we can use one fan, but there are cases where we require to use more than one fan. And in most of these cases, there are cases where we need to overcome higher static pressures or to supply more volume of air. So just to summarize kind of the reasons, the total required airflow may be high, or the pressure may be high, the power may be high, and so in those cases we need larger fans. Another advantage of using multiple fans is cases where producers want to turn off some fans to operate at lower airflow rates. So there are those cases where we need that flexibility to operate at lower airflow rates, and therefore we need that flexibility of turning on those fans as necessary. There are also cases where we are restricted by the current that we want to draw from the line. When we have bigger fans, we need to draw higher currents to start with. But if you have multiple fans, it's possible to start one fan at a time, and by so doing, we end up having lower starting currents. I want to take you through some fan selection techniques. There are 4 major steps. The first step is to, first of all, calculate the required total airflow rate. The second step is to estimate the static pressure in your system. then we need to go through a calculation that helps us to determine the power that we need for our fan. The last case is where we now go into the manufacturer's manual and we select a suitable fan that can achieve our drying purpose. And so the first step is to determine the total required airflow for your process. So there are various processes that we encounter. It could be an aeration process, it could be a dry aeration process, a natural air drying process, a low temperature drying process, layered drying process, a batch in-bin drying process, a continuous in-bin drying, or a continuous flow drying process. All these drying processes require different minimum airflow or airflow ranges. If we are going to do a natural air drying process, we require airflow rates between 1 and 3 CFM per bushel. In the next step, we need to obtain the static pressure that the fan will overcome. The static pressure, as we've noticed, is dependent on the grain type, dependent on the grain depth. It's also dependent on the airflow rate that we are pushing through the system. If the grain depth is 10 feet and we decide a design airflow rate of 1 CFM per bushel, we would expect a static pressure of 2.1 inches of water column to be developed in that system. If we double the grain depth to 20 feet, we would expect a static pressure at the same airflow rate to be 8.41 inches of water. So naturally, doubling the depth does not necessarily mean a doubling of the static pressure. The static pressure increases several folds by just doubling that grain depth. In approximation of the required fan horsepower, we have to go through our calculations. And this equation here shows us how to go about that. The fan horsepower is the same as the airflow, CFM per bushel multiplied by the static pressure in inches, all that divided by 6,356 and the efficiency of that fan. Doubling the CFM per bushel airflow rate on the same depth of grain requires 5 times more horsepower, and doubling the grain depth at the same CFM per bushel requires 10 times more horsepower. Once we calculated the power that we require, the next step is to verify the performance data of that fan and select a fan that is performing at slightly higher power compared to what we calculated. So to be able to understand some of these steps, let's go through some of examples here that help us put all this together. So in this case, we have a bin that has got a diameter of 42 feet, and the grain that is put in there is stacked to a depth of 20 feet. The grain type is rice, and our process here is natural air drying. And so the design airflow is 1 CFM per bushel, and you can go all the way up to 3 CFM per bushel, again dependent on the moisture content of the grain in that bin. To calculate the airflow, we need to calculate the volume bushel of rice, and then we need to multiply that by the design airflow. And to be able to calculate that volume, if we know the diameter of that bin, we can calculate the area and multiply by the height. That's going to give us the volume. Now, we need to remember that that volume is going to be in feet, or in cubic feet. But our design airflow rate here is in cubic feet per bushel. So we need to convert that volume into bushel volume. And to be able to do that, we need to remember the relationship of 1 bushel is the same as 1.244 cubic feet. And that's where that constant 1.244 is coming in that equation. If you do that calculation right, you'll realize that the total air volume is going to be 22,264 cubic feet per minute. So once we do that, the next thing is to calculate the power that we require for our fan system. So from the airflow resistance table for rice at 1 CFM per bushel and 20 feet grain depth, we find that the static pressure is going to be 8.41 inches of water. And so using the equation provided there, we multiply the airflow, multiply that by the static pressure divided by 6,356 and the efficiency term, and assume that efficiency to be 50%, we find out that we require 60 horsepower to be able to overcome that static pressure. Again, most funds will come with information on the efficiency. And so we find that we require a fund that can provide 60 horsepower to be able to overcome the static pressure in our system. We are faced with a choice of picking one fund that can give us 60 horsepower or picking two funds that can give us 30 horsepower and another 30 horsepower, or using an axial fund or not. So there are various considerations that we need to go through. Number one, we need to verify the performance data and choose the fund having a motor rated just slightly higher than the value of the power that we have calculated. Then we need to consider the static pressure to be overcome, the cost impact of choosing an axial fan or a centrifugal fan, or choosing either a single fan or two fans that can provide us the required power. Now, lastly, if the intended fan supplies more than the required airflow, then a smaller size fan should be considered. I want to leave you with some references here that you can look at and get more details in some of the areas that we have covered in this module. And with that, I want to say thank you very much for listening to this module, and I look forward to talking to you in the subsequent module. Thank you.